With computer audio. Start video. Mohammed's with us. Okay, Thursday, October 15th, 2020. All right. Thermodynamics. Let's see who we got here. We have a good crowd. Nicholas, Alex, Julian, Mohammed, Nathan. There's another one here down here. I can't read it. Julian. I have trouble reading the last. William's with us. William, Julian, Reagan, Nicholas, Mohammed. Got a good crowd. Well, let's see what time it is. Oh, gee, it's time for class. Class is starting. Do you have any questions for me? Go ahead, I'm listening. Well, okay. What are we going to study today? Let me look and see here. I think that you have a exam 2. Let me look at that. Yeah, on my calendar here it says, gosh, this is due tomorrow. You've had this thing. This exam is due tomorrow. It's exam 2. Were you able to pull it up okay? Somebody say, uh-huh.
Uh-huh.
Yeah, you're able to pull it up okay. It's chapters 3 and 4. And it's due tomorrow night, which is Friday. Now, what about homework? I wonder if there's any homework. Let me look and see. Today's the 15th. And it says here the 15th. It says chapter 5, problem 19. Homework assignment number 16. It's problem 519. Didn't give the page number. Let me see if I can find that. Totally organized here as always. October 15th. Page 41 it says. So you've got that take-home exam to turn in tomorrow night. You've got your homework. But what are we going to talk about? Well, we're supposed to talk about thermodynamic cycles today. But maybe I was thinking we could have a quick review over some basics, and then we'll talk about cycles. That sounds good to me. Unless you have a comment or question, I'm listening. Well, okay. Now let's do a kind of a review here. Let's suppose you had air. In a polytropic expansion, with a polytropic constant equal to 1.25. And we're going to go from 300 kilopascal, 360 Kelvin, to 100 kilopascals. So that's our problem, but what are we supposed to find? Well, we could find, we could do a lot of stuff. We could do the device sketch. It's in a piston cylinder. Let's make a note of that. It's in a piston cylinder. And we can do a device sketch. We could do a PV diagram. That'd be good. We could find the final temperature, the work per mass, and the heat transfer per mass. So there's quite a lot of wonderful things that we can do with that. So let's do it. Have a little review session, then we'll talk about cycles. The topic for today is going to be cycles. Well, they're thermodynamic cycles. We're not talking about motorcycles or other kind of cycles. All right, well, first thing I think would be the device sketches. So let's see what those would look like. Is the pressure going up or going down? What do you think? Pressure going up, pressure going down. Looks like the pressure's going down, huh? What happens when the pressure goes down? Well, I think you have to take that weight off and the piston will go up and the volume will increase. There you go. And right now it's state 1. This is state 2, and we have air in there. And the temperature here is 360 K. And the temperature here, well, we don't know. Well, why don't we find that? Now we have a beautiful equation for ideal gases like air that are in polytropic processes, and they go like this. You want to have that written down someplace in your notes or wherever that you can grab it there. It's a nice little equation. Be careful now. You can't use that on anything. It only works if you have a polytropic process and you're dealing with an ideal gas like air. Air behaves like an ideal gas at these temperatures and pressures. So let's put our numbers in. We're going to solve for T2. T1 is 360. It's got to be in Kelvin. P2 is 100. P1 is 300. N is 1.25. Okay, I'm going to be quiet for a minute. I want you guys to find that. Find the temperature at state 2. It's going to cool off. You know that because when you remove that weight and it expands, air cools off. And then I'll call on one of my excellent students here. Go for it. If you tuned in late and you wonder what we're doing, we're going to talk about cycles, but right now we're just having a little review of stuff we already know. And we're finding the temperature at state 2. And I'm going to go to one of my excellent students here. Reagan, let me pick on Reagan. Unmute, Reagan, and say hello, please.
Hello.
Hello. Reagan, did you get that temperature at state 2 yet?
No, I'm almost there. I'm
Okay, take your time. I can wait.
close. It's 1.25 minus 1, right? On the top.
Yes.
Okay.
Well, we need to move on. Reagan, did you get that yet?
Yeah, I'm done. I'm almost done. Almost. Just 1 second. I'm not sure about my answer. That's why I'm kind of like.
Well, I got an answer. I think mine's right.
I got like 0.26.
Nope, something bad happened.
Yeah,
Maybe
that's
you need to flip that.
Do we have the T2?
Well, that's what we're trying to find. We're trying to find T2.
Okay, that's why.
We're trying to find T2.
Okay, I think I made a mistake. I have to fix that.
Hey, you're human. Well, Reagan's still working on that. Let me pick on somebody else. Nathan, unmute and say hello, please. Earth calling Nathan.
I'm right here.
Yeah,
I'm right
Nathan,
here.
What'd you get for T2?
Okay, so I'm limited with what I have right now. I don't have my calculator, but it's 120 to the 0.2 power. I have that much.
Yeah, this is 0.2. You got that. But 100
120.
over 300 is 1/3. What did you say?
I had 120 to the 0.2 power.
Not 120. 100 over 300 is not 120.
Okay.
And who did I just talk to? I lose track of what I'm doing here. That was Nathan, wasn't it?
This is Nathan. Let me check my notes again.
Well, don't feel bad. That's what
It
we're
did.
here for. Hey, go back to my other friend, Reagan. Reagan, what'd you get this time? Reagan's not answering me.
Oh yeah, I got 1.4 this time. I don't know what
No,
exactly I'm doing.
something bad happened.
What problem are we doing? You say homework
Well,
16.
we've got an equation here, Reagan, and we're
Mm-hmm.
trying to solve for T2.
I don't know. Okay.
If you want, I can write it out nice for you. T2 is going to equal to 360
Mm-hmm.
times 0.3333 to the 0.2. See, this exponent turns out to be 0.2.
Uh-huh.
I think Nathan just told us that a minute ago.
Yeah.
And 100 over 300, that's 0.3333. So you put that in your calculator and you'll get your answer. So what do you get when you do that?
I got 40.0.
Something bad happened. Something bad happened. That can't be right.
Professor, this is Nathan again. But can anybody confirm or that this is wrong? It's 120 to the 0.2 power. Is that not right?
You have to take this to the 0.2 power.
Mm-hmm.
Then you multiply by the 360.
Oh, sorry. I understand now.
You know
I'm
what
with you
you
now.
did?
Sorry.
You
Yeah.
did that.
Parentheses. Parentheses are important. I got you. Yeah.
Yeah, they are. And that's why we're doing this.
So I got 289.0.
Good going. Yay.
Yeah.
Yay. It's I'm just going to round it off to 289. 289. Hey, cooled off. See, it was 360 and now it's 289. But see, I'm glad we did this because it's simple little goof ups like this business here. See, one of my excellent students put the brackets around here like that. Well, that's not right. That's not right. You do this, and then you multiply. So hopefully that's how you learn. Okay, well, now that we got that temperature, let's draw the PV diagram. I need a little room now, but we got our new temperature now. And I need some room here. And I don't want to lose anything, but we know we have a polytropic N equals 1.25 polytropic process. We know the pressure goes from 300 to 100. Let me write that down. So we have the pressure, we have the temperatures. I can erase it anymore. And you guys know there's an exam that's due tomorrow night at midnight. That'll give me something to do over the weekend. I can grade those. But now let's do the PV diagram. We've got to know how to do these PV diagrams. I graded some homework here yesterday afternoon, and people were putting vapor domes where they don't go, and they were leaving out vapor domes where they do go. See, this is air. You don't put a vapor dome in here. There's no vapor dome. It doesn't turn to a liquid. It stays a gas the whole time. Now I'm going to be quiet for another minute, and I want you to draw the process. And here's another thing. My students are doing these PV diagrams, but they're not putting the process in. See, the process is the most important part. You leave the process out, and what good is it? So I'm going to be quiet for a minute. I want you to draw the process. You know everything. You know the temperatures and the pressures. It's air. Okay, go for it. I'll be quiet and let you try that. Well, let's see what they look like. Now you're dealing with an ideal gas, and isotherms kind of go like this. The hot ones go like that. That's your 360K. And then the colder ones go like this. This is your 289K. Hey, that's a pretty big change in temperature. You know what that is? That's it cooled off 71 degrees. That's a lot of temperature change. Now the pressure went down. It went from 300 kilopascal to 100. And this is what I want to see. I want to see the process. See, here's 1, here's state 2, and here's your process, like that. There you go. With an arrowhead on it. That's the process. That's what I want to see. Some of you are leaving out the process. It's also nice to have isotherms on there. It's nice to label this. We could even calculate the specific volumes at 1 and 2. We could do it. Hey, it wouldn't hurt us. Let's do it. Here goes. You go P1 V1 is equal to RT1. We know P1. It's 300. We know R and we know T1. So we could get V1. And we could use the P2, same thing, P2 V2 is RT2. We could get V2. Again, I'm going to be quiet for a minute. Let's get those. That won't hurt us any. Let's get those and I'll label them and put them in there. Go for it. Find the specific volumes. Well, here's what I got for my specific volumes. Envelopes. This is 0.3444, and this one is 0.8294 cubic meters per kilogram. So see, you can put a lot of information on your PV diagram, but you don't want to forget your process. That's the most important thing of all, is the process. There it is. There's a one, state two. And you draw the process. There it is with an arrowhead on it, on the end of it. That's what I want. Now, let's suppose we wanted to find the work per mass, little w. We have a lovely equation for P2V2 minus P1V1 all over 1 minus n. Hey, we know everything. We know P2 and V2. We know P1 and V1. We know the whole works there. We can get the work, and I'm going to be quiet for a minute, and I want you to plug that in and get the work per mass for me. Go for it. See if you can do that. I know I'm rushing you, but I thought I'd ask. What about my friend Alex? Alex, unmute and say hello, please.
Hello. So I had a question.
Did I,
What was in?
have I picked on you already today, Alex?
You might have. I can't remember. I was in your strength class too. So
Oh, yeah, that's what it was. I think I picked on you in the other class. Well, I thought I'd ask you, have you figured out this work per mass yet?
what was in?
N is called the polytropic constant.
And was it 1.25? Was that it? Okay.
Yes, it's 1.25.
I was looking through
And
my
make
notes.
that
I
very
couldn't find
clear.
that one.
It's
Let me type it in
1.25.
to the calculator.
1.25. There we go. I guess I didn't give you enough time.
I got 81.52. I did it real
Well, that's
quick.
what I got.
Okay.
I got 81.5. Now, Alex, what's the units on that?
Oh boy, I didn't have time to work through the units, but
Well, take a wild guess.
I'm drawing a blank. I'm not gonna lie. I know that this is little w, so it's not the same as big W, but
No. See, if it was big W, it would be in kilojoules. But this is little w. So what would it be?
Is it like kilojoules over like mass? Is that right?
Yeah,
Okay.
it's kilojoules divided by what?
Just kilogram.
Yeah, there you go. Kilojoules per kilogram. Good going. Yay. We just figured the work per mass. Now, if you were to make the area under here, see, you could color that area. You can make it pretty. Here, let me color it green. Here we go. You could color this area green. See that green area there? That area is equal to 81.5. The area under your PV graph, it gives you the work. Well, it's P little v, it gives you the work per mass. If it was a P big V, it would just give you the work. So we did great. We got the work per mass. Now let's get the heat transfer. And I need some room here, though. Here's some room up here. There's lots of room. Now to find the heat transfer per mass, I wonder, let me ask one of my excellent students. Let me go to Braxton. Braxton, unmute and say hello, please.
Hello.
Yeah, Braxton. How do you find the heat transfer per mass, Braxton? Got any ideas?
There was an equation. It was like something equals Q minus little q minus little w.
That's it. That's it. He's got it. You've got an equation that goes like this. Braxton, that equation has a name. It's the most important equation in our course. What's the name of it?
Oh,
I'll
is that
give you a hint. It's,
first
ahead.
law? First law of
yeah,
thermodynamics?
that's it. Good going. Yay, it's the first law. Now you got to be careful. That's the first law for control masses. But see, we have a control mass. No mass comes in and no mass gets out. It's a control mass. Now, if you have a mass coming in and mass going out, you got a different first law. Like with a nozzle, for instance, or a throttle or a turbine, it's a different first law. But this, we studied this a while back. Kind of interesting. Well, let's get it. This sounds like fun. Let's find the, well, what we're going to do is we're going to find the heat transfer. Now we have a lovely equation for that delta U. It goes like this. It goes C sub P delta T equals Q minus, we know what the W is. We just figured it out. It's 81.5. So here's our equation. You're going to have to look up C sub P for air and solve that. I'll give you another minute and we'll find the heat transfer. Go ahead, I'll be quiet. Well, I wonder if anybody's got that. What we're trying to find right now is what the heat transfer is. Let me go to my friend here, Brian. Brian, unmute and say hello, please.
Hello.
Hello. Hey, Brian, have you figured out what this heat transfer per mass is yet?
No, sir.
That's okay. Here, let me give you a little help. That C sub P is 1004 kilojoules per kilogram Kelvin. That's what it is. And the change in temperature is minus 71 degrees, right? If you subtract here, I think you get 71. It got cooled off. Yeah. So now you can solve this and solve you can do it, Bryce. Am I still talking to Bryce? I forgot who I was talking to. It's Bryce, right?
Well, I think you were talking to Brian.
Oh, I'm sorry. I got mixed up. Well, who am I talking to now?
This is Bryce.
Bryce. Bryce,
Yeah.
have you figured out what the heat transfer per mass is?
Yeah, 10.216 kilojoules per kilogram.
That's exactly what I got. Let me write that down someplace. The heat transfer per mass is 10, I'll just round it off, 10.2 kilojoules per kilogram. Now it's plus, and I'm talking to Brian right now. If you have a positive heat transfer, Brian, does that mean that you got a heat transfer into your air in that piston, or does it mean that you have a heat transfer out of the air in that piston? Brian, you got a 50-50 chance of getting this right. Which is it? Is the heat transfer going in or out?
So it's positive.
It's positive, so does it go in or out?
I think it's going out.
Oh, Brian, don't go to the casino, Brian.
Okay.
You had a 50-50 chance and you blew it. Positive heat transfer is in.
Oh, okay. I'll remember that now.
But I'm glad we did that because we got to know that. Heat transfer is either you're transferring heat out or you're in. Now, let me give you an example, Brian, and the rest of you. If I go outside in the wintertime and it's cooling off, there's supposed to be 40 degrees tomorrow morning. I don't know if you've heard that. Let's say I go outside and walk around with my dog in the morning at 40 degrees. And then I come in and I shake one of your hands. Well, my hand is cold because I've been out there in the 40 degrees. And you're in a nice warm house, your hand is warm. Which way is the heat transfer going to take place? Is heat transfer going to go positive to my hand, or is it going to go positive to your hand? Think about it. Well, you know the answer. I'm going to get warmer. I'm holding your nice warm hand, and heat transfer goes from you, who's warm, to me, who's cold. And so the heat transfer is positive for me, but it's negative for you because the heat transfer is it's leaving you. But in this case here, the heat transfer is positive. So we're going to draw it going into your air there. And so really there's two reasons why this expands. One is that you took some mass off and you make the pressure smaller. Well, that makes it expand. And the other is you are in a way like putting it on the stove and heating it up. And when you heat air up, it expands. So there's two reasons why it expanded. Now, if you didn't have any heat transfer, they have a special name for that. I wonder if anybody can remember that. When you have a process, let me go to one of my students here. We'll pick on my friend Mohammed. Mohammed, unmute and say hello, Mohammed.
Hello.
Yeah, hello. Hey, Mohammed, if there's no heat transfer at all, if the heat transfer is zero, what's the special name for that?
You want to, you mean the process?
Yes.
Is it isobaric?
No, that's constant temperature. No, it's not isobaric. No, I said it wrong. Isobaric is constant pressure. We're talking about no heat transfer. It has a special name. Mohammed, what is it? I'll give you a hint. It starts with A.
Starts with A?
Starts with A.
Adiabatic process?
That's it. He's got it. Mohammed's got it. It's called adiabatic process. It starts with A. Adiabatic. Well, we don't have an adiabatic process. You know, if we did, I think it would be colder. I think our process would look like this. We know it goes from 300 to 100. The adiabat, I wonder if I could use a different color here. Maybe this green will show up. The adiabat would look like this. Does that show up? Yeah, pretty much. See, we went from 300 to 100 kilopascals, but it's going to be colder. It's going to be colder because, see, this isotherm here is colder. It's colder than 289. It's colder. How come our process is warmer? Well, it's warmer because somebody is transferring heat into our air. They put it on the stove. Well, that'll make things warmer. But see, if you had it insulated and there's no heat transfer in or out, and all you did was take this mass off, your process would do this. Do you understand? You'd still go from 300 to 100, but your temperature would be colder. Well, we really worked that problem to death, I think. It was good. Do you have any questions about that?
Professor, I think I might have a question.
Yeah.
So in this problem, you showed how to find T2 with an ideal gas using that it's like that equation. It's like the ideal gas law combined with that polytropic process.
Yes. Yes.
However, for a non-ideal gas, we can't use that equation. Is that correct?
That is correct. Do not use that equation unless you have an ideal gas. Who am I talking to?
This is Bryce. I'm just
Hi,
trying to
Bryce.
figure out how would we approach a non-ideal gas if we are not allowed to use that equation.
You use the tables, Bryce.
Okay.
You use you might have to interpolate.
Okay. What about, so when you were finding the polytropic constant or the N value, that's not in the tables, correct? How
No,
would
it's
we
not in
approach?
the tables. That is correct. Now, we didn't have to find it in this problem here that we did together. it was given. It was 1.25. It was 1.25.
Okay.
Let me show you one other thing. As long as Bryce brought that up, I need some room here. And I'll explain this more later. But if you had an adiabat, which we don't have an adiabat. We have a heat transfer in. But if you did have an adiabat, it turns out the polytropic constant for air is 1.4. There's tables of these, and let me just show you what that temperature would be. You want to call it maybe T colder, we'll give it a name here. See, I drew it for the adiabat. The beginning temperature was 360. The pressures were, the final pressure was 100. Initial pressure was 300. But see, for the adiabat, it's 1.4 minus 1 all over 1.4. Okay, we're going to take time out and we're going to find this temperature. This will be good practice because a couple of you had trouble with that a little while ago. I'm going to be quiet and we're going to find the temperature if the process had been an adiabat. I drew a green process here. Go ahead, find what the temperature would be with the adiabat. I'll explain why this is 1.4 another time. We don't have time today. Go for it. Now let me go back to Reagan. Reagan was having a little trouble with this. Reagan, unmute and say hello, please.
Hello.
You were having a little trouble with this equation earlier. Of course, we had different numbers here.
Mm-hmm.
Can you get it this time?
Yes, I believe I can.
I'll wait. Go for it.
Okay.
I have faith in you, Reagan. I know you can do it.
Yes, I can.
Good attitude. I've got an answer. I'm not sure it's right, but I've done it.
All right.
Here, I'll write it out for the rest of you.
I got 263.0.
Yay, that's what I got.
Good.
I got 263 Kelvin. Hey, see, it's colder. If you had an adiabat, the process would do this. See, I'm drawing the process here for the adiabat. That's the adiabat process. And it turned out to be colder. It's 263. Well, that, you know what? 263 is colder than 289, isn't it? Oh, yeah. It's, what, 26 degrees colder?
Mr. Griffin,
Yes.
I have a question.
Yeah.
So if we have a gas like ammonia or nitrogen, and we know the pressure P1 and P2, and we
Yeah.
are required to find the polytropic constant N for that
Yeah.
non-ideal gas, what equation will we use to find that N value for ammonia or
You
nitrogen?
would use this one, Mohammed. Make a little room. Well, there's some room down here. You'd use this one. That's it. In fact, that's really that's really the definition of what a polytropic process is. P1V1 to the N is equal to P2V2 to the N. So what you need, Mohammed, is you need P1 and V1 and P2 and V2. That's what you need.
And what after putting, if we get a value of N equal 1, so does that mean we are doing okay or not? If we get a
No,
value
it
of
means
N.
you're fine. N can be anything. It could be negative. It can be
Okay.
0. It can be, pick any number you want, Mohammed. It can be anything.
Would N equals 1, would that be an adiabatic, would that mean that it's an adiabatic process?
No, it doesn't mean it's an adiabatic process. If you have air, an adiabat has a polytropic constant of 1.4.
Understand.
Okay, we're going to move on to our next topic. Unless there's another question, go ahead. I'm still listening.
Yes, I do have a question.
Yes.
I'm having a trouble to work homework chapter 5, problem 19.
Okay.
Can you please, like, if we do have time, work the same problem, like the problem look close to that?
Let me see what it is first. Now, this is my friend Reagan again, right?
Yes.
Okay, 519. All right. You're going to need this topic that I'm going to talk about, Reagan, right now
Okay.
in order to work that problem. So let me talk about cycles, and maybe it would make more sense to you after I get through, because you need the information I'm going to give you. There's 3 kinds of cycles. There are 3 different cycles. And the reason why you're having trouble with that problem, Reagan, is we haven't discussed that yet. But here they are. There's power cycles. There's refrigeration cycles. And there are heat pump cycles. Three different kinds of cycles. Now, Reagan wanted help on 519. That 519 is a power cycle. We'll talk about it first, but I need to tell you about all 3. Now, power cycles, they have diagrams in the book of power cycles. Let me find one here. Just a minute, I got lost. This would be chapter 5. And here's a power cycle on page 145. Now there's another name for a power cycle. Another name is a heat engine. means the same thing. And an example would be like your lawnmower. Your lawnmower is a heat engine. Well, your automobile is a heat engine because you've got fuel, you're burning fuel, it makes a high temperature, right? It gets hot. And you have a cycle. Now there's a diagram of the cycle on page 145, and they have a boiler. And then they have the turbine. We've studied turbines. We've done some homework on turbines. And then we have a condenser. I think we did a condenser too. It's a form of a condenser is just a form of a, oh gee, my mind went blank. Somebody help me. Condensers are just a type of heat exchanger. Condensers are just a type of heat exchanger. And then you have a pump. And then you have the boiler, and around you go. So it's on page 145. And what happens is the turbine gives you power. Power is W dot. See, you come in here with liquid. You've got liquid here. And the boiler evaporates that liquid, it boils it, and you've got steam coming out here. Like if it's water, it's steam. But if typically you got water. So steam's coming out here. And it goes through the turbine, turns the turbine blade, gives you power. And then it goes through the condenser, and the condenser cools that off, and it condenses it to a liquid. So you got a liquid coming out of the condenser, but see, it's at low pressure. The pump increases the pressure and sends it to the boiler. The boiler boils it, and around you go. Now they have a diagram, a schematic for this. And there's some room over here. There's enough room right here. It's clockwise. You always draw the heat engine clockwise like this. And you have a high temperature here. And then you have a low temperature here. And you have power coming out here. And what you have right here is a heat transfer. It would be a QH dot. It's a heat transfer. Well, it's per time. You've got over a period of time, you're transferring heat. And here's a heat transfer at a lower temperature. And you got your power here, that's W dot. So here's the schematic for a power cycle. Now a refrigeration cycle, let me find one of those. Here's one here. This is on This is on page 147. And they drew a compressor. They didn't draw this compressor right, but I'll forgive them. And here's your evaporator. And coming out of the compressor, you've got your condenser here, kind of running into my page number there. And then here, what you have here is your expansion valve. Notice you're going around and around counterclockwise. It's counterclockwise. This is a compressor, like a refrigerator. I think we've done a compressor problem. I believe we have. And see, this is why you have refrigerators. This evaporator, that cools off your car or your house or your hot dogs or whatever it is you want to cool off. It takes heat transfer away from your milk or whatever and sends that energy into your refrigerant, whatever that is, ammonia, R134A in the case of your car. And see what this is your QL dot. And then there's a heat transfer out here. That's your QH dot. Ever walked by your friend's apartment house and there's an air conditioner sticking out the window, and as you walk by it, it's blowing hot air on you? Well, that's the condenser. If you have an air conditioner outside your house, go stick your hand on top of it. It's blowing hot air. That's the condenser. See, inside you've got an evaporator. That's cooling off your house. It's removing heat energy from your house, keeping your house cold. And the condenser outside is giving that heat energy to heat up Oklahoma. Well, notice it's counterclockwise. So the schematic or the diagram for the cycle, the cycle, what I call the cycle schematic. And now what I just drew you was on page 147, if you want to look in your book. But if you're doing a refrigeration cycle, the cycle schematic looks like this. You go around and around counterclockwise. And here you have a QL dot. And here's your low temperature. And here you have a QH dot. And here you have your high temperature. Well, there's your, and here, now here's the difference. You have to input power to have a refrigeration cycle or a heat pump. In fact, the cycle schematic, let me write that for you. This is the cycle diagram, or I refer to it as the cycle schematic. It's counterclockwise, and it's the same for both of these. It looks like that. It goes counterclockwise. Power has to go in See what this is? It's a plug. You got to plug this thing in for your refrigerator at your house. There it is. There's your plug. Unplug that refrigerator and guess what happens? Well, your milk gets warm, your bologna gets warm. You're going to have to throw some stuff out. Stuff will spoil. It requires power. See, a heat engine provides power. Let me write that. It provides power. But a refrigeration cycle or a heat pump, both of them, they require power. All right, now we're going to talk about efficiency now. Are there any questions? Any questions so far? Okay, all these devices have something called either a efficiency or a coefficient of performance. And with this information, my wonderful student will be able to do that problem 519, I bet. So we're going to talk about efficiency. Now, power cycles have efficiency. The symbol is a eta. Refrigeration cycles, they don't have efficiency. They have a beta. It's called a coefficient of performance. Heat pumps don't have a beta. They have a beta prime, but it's also called a coefficient of performance. Now let me give you those, but I just need some room here. Here's some room right in here. Look here. Here's some room right in here. We don't need this. We know it's October 15th. We know it's 2020. We know we're studying cycles right now. We're talking about something called efficiency. Now, power cycles, the other name for a power cycle is a heat engine. But power cycles have efficiency. They use a Greek letter eta. It's a Greek letter eta. Is that right? Yeah, I think that's right. That's it. It's Greek letter eta. And what it is, efficiency is always something you desire divided by something that's costly. You have to pay for it. Now, for a heat engine, what you desire is this power on your lawnmower. Now a lawnmower actually has a heat transfer to the environment. If you put your hand on the exhaust, chugga chugga puff puff, chugga chugga puff puff, that exhaust is blowing hot air on your hand. Try it sometime. Well, the same with an automobile. Put your hand on the exhaust pipe of an automobile while it's running, and it's blowing hot air out the exhaust pipe. But that's not what you bought the lawnmower for. You didn't buy that lawnmower to keep your hand warm. You bought it to cut the grass. So what you desire is the W dot. Efficiency is always something you desire over something that costs you. Well, guess what costs you? It's this QH dot. You got to go down to Quick Trip and fill your little gallon tank with gasoline, and it's going to cost you some money. They don't give it away. You've got to pay for it. It's going to cost you. This is the equation for the efficiency of a power cycle. Now, according to the first law, the first law for a cycle says that the sum of all the input power has to equal the sum of all the heat transfer rates. So in this case here, you could write the power is the heat transfer QH dot minus the heat transfer QL dot. If you divide by QH dot, you get a nice equation for the efficiency of a heat engine or a power cycle. It's equal to 1 minus QL dot over QH dot. Do they have an equation like that in your book? Let's look and see. We're getting now to where my excellent student can do problem 519, I bet. Yeah, there it is. I see it. I see that equation. Let me see if I can see it another place here. They usually at the end of your chapter have a whole lot of equations. Let me see if I can find it here. Yeah, it is. I just found it. I found this equation on page 171, but they did it without the dots on it. What they have is QL over QH, which is fine. It's just that with the dots, you're talking about rates. Without the dots, you're just talking about the heat transfers, not the rates. See, rates are per time. But that same equation's there. Okay, how are we doing? Well, we got 5 minutes left. Let me talk to you about the coefficient of performance for refrigeration cycles. Any questions or comments so far? Okay. Well, I need the room here. We'll say goodbye to that for just a minute. Now, this is the same idea. It's efficiency, but they don't call it that. See, efficiency is always less than 1, but this thing we're going to talk about here, the coefficient of performance, the COP, it's always greater than 1. Now what it is for a refrigeration cycle, let me put refrigeration cycle here. It's something you desire over something that costs you. It's the same idea. Now, what do you, on this refrigerator here, you got to plug it in. And see this, what this is a heat transfer rate. It's removing heat from your hot dogs. And what this is a heat transfer rate at a higher temperature. That's, did you know that your refrigerator actually warms up your kitchen? When the compressor comes on, you'll hear a click, and then you'll hear a whir. You'll hear a fan motor, and it's blowing warm air down out the bottom of your refrigerator. Go to take your shoes off, go barefooted. When they hear that click and you hear that whir, you'll feel warm air blowing on your toes coming out of the bottom of the refrigerator. That's what this is. That's not why you bought that refrigerator. You didn't buy that refrigerator to keep your toes warm. You bought it to remove heat from your hot dogs or whatever you got in there. So what you desire on your refrigerator is your QL dot. Now what costs you? Well, this is what costs you. You got to plug it in. You have to pay PSO for the electricity. Now again, you can write that W dot as QH dot minus QL dot. You got a QL dot in the numerator, and see if you can find that equation. Boy, Joe, I see it. It's on page 171. only they write it like this. They say the beta is equal to, for a refrigerator, it's equal to QL over QH minus QL. Put the dots on there and they'll have what I have. Okay, we got one to go, and that's the heat pump. Read about this stuff. We'll talk about it some more next time we meet, but let's do the heat pump. There's some room right in here. There we go. Now, I don't have a heat pump at my house. Heat pumps have an advantage. You see, you have an energy input here and an energy input here. This energy input is free because it's removing heat from the environment. So on an expensive heat pump, they dig down several feet down into the ground. Did you know that the temperature, if you dug down in the ground maybe 3 or 4 feet, did you know that temperature stays pretty much the same all year round? Even in the winter, it might, sometimes it gets below 0 degrees here in Tulsa. Not very much, but it has happened. But if you dug down 3 foot down in the ground, it's warmer down there. It's warmer down there. Okay, now we're going to do the coefficient of performance. It's abbreviated COP. Oh, gee, I'm running out of time. It's beta prime for a heat pump, and it's what you desire. But see, a heat pump, this is what you desire. You're trying to keep your house warm. Heat pumps are to keep your house warm in the winter. And then in the denominator, you have to pay for this power input. You got to plug that into PSO. Well, I think we've had fun. I bet you can do that problem now. Here's your last chance to say anything. I'm going to sign off here momentarily.
I have a question, Professor.
Yes.
So on problem 19, did the problem require the PV diagram or you just work the problem? This way.
No. What I really wanted, I didn't explain that. Thank you so much for asking. I want you to draw the schematic diagram, the cycle diagram. You don't
Okay.
have to do a PV diagram. Thank you for asking.
Okay, appreciate it. Thank you.
Yeah, draw the cycle diagram. Anybody else? We're going to say goodbye. Okay, bye-bye, students. See you, what, Tuesday at 9? No, at 11. See you Tuesday. Is that right? Tuesday at 11, yeah. Adios, muchachos. You're supposed to say adios, Professor.
Adios.
Yeah, see you later.
Adios.